Hi everyone, welcome you to today's lecture. This is a presentation on we're solving examples using thevenings as well as Norton. In this series, we'll just look at a solution using thevenings, whereas in the next one, we shall continue with the Norton's theorem. Okay, so this is an example. The question is saying calculate the current across the 6 ohm resistor using A, Thevenin's theorem, and B, Norton's theorem. For this presentation, we just look at the A part of the question. As in the next presentation, we'll do the same question using Norton's theorem. So, this time the circuit has been given. We've got 2 voltage sources, 4.5 volts and the 3 volts there, and we've got 3 resistors. Okay, this time our load is this 6 because we are calculating the current across this. So we treat this one as our load. So they want us to change this circuit from whatever it looks to something which is like this. Something which just has a voltage source which is in series with a resistor. Okay, so our voltage source will be the Thevenin's voltage, and our resistor, equivalent resistor, will be the Thevenin's resistor, like that. Once we have that, then you will connect back the 6 ohm this side. Okay. So our task here is to find the RTH and VTH. How do you find the RTH? RTH, which is the Thevenin's resistance, is found by you remove the voltage sources by short-circuiting them and current sources by opening them. In this circuit, we don't have current sources, we only have voltage sources. So you remove them in the circuit by short-circuiting them. The first step is you remove the load, which is the 6 ohm. Upon removing that, disconnect the voltage sources by short-circuiting them. So when you remove this 4.5 volts, you remain with a short. Then this resistor will remain. Okay, this one has been removed, it's not there. Or rather not even right, because this resistor has been removed. And we have another one here. Okay, this side where there was a voltage source, you just short circuit it. And our circuit will remain like that. Where you only have 2 resistors, the 4 ohm and the 2 ohm resistor. Upon having that, find the equivalent resistor of this circuit. So the equivalent resistor, which is the Thevenin resistor, will be, these are just connected in series. So it's a series combination of the 4 as well as the 2, and you remain with the 6 ohm as the equivalent of Thevenin resistor. So the Thevenin resistor has been found there, which is 6 ohms. Okay, our next task is to find the Thevenin's voltage. How do you find the Thevenin's voltage? So we calculate the Thevenin's voltage by viewing our circuit from a point where the load is connected. So this circuit, the load is connected at this point, this 6 ohm. The load is connected here. So we want to find the voltage across that point. So let's call this point as VTH, because that is the Thevenin's voltage, which is across the 6 ohm resistor. So how do you find this? You can imply any of the rules in which you use to find circuits. Okay, so you can realize that this is a battery terminal where you have a positive and a negative, and this is a battery terminal where you have a positive and negative. So you've got a current which is going this side, entering this node, and you've got a current going that side, entering that node. You're supposed to have a current going like that, but since the load has been disconnected, so you have this current as 0, there is no current actually going there. So, using the given rules, Kirchhoff's current law, you realize that you've got a current entering and current leaving, which is a 0. So, the summation of currents entering is equal to the summation of currents leaving. Currents entering, you have this one. So, you've got 2 voltages here. You've got this voltage and that voltage and the resistor there. So for current to go this way, it means this voltage is at the higher potential as compared to that one. So you're going to have this 4.5 volts minus this Thevenin's voltage. Let's get rid of the units. So 4.5 minus the Thevenin's voltage divided by 4, because that is the current. Current is voltage over resistance, but you've got two voltages there, the voltage at the higher potential and the other one at the lower potential. So it's the difference in the voltages, which is voltage divided by the resistor involved, which is the 4. So this will be the current going this side. This current plus the other current is this one. Current is voltage over resistor. So for this current, we've got two voltages involved. Voltage at this higher potential and this one at the lower potential. That's why it's going like that, because this one is at higher potential. So you've got 3 volts minus the Thevenin's voltage divided by the resistor involved there is a 2. They're supposed to give us the current leaving that node, which is, there's no current actually given because it's an open circuit. So it's a 0 amp. Okay, you have that. Upon having this, we can get rid of the fractions by multiplying these expressions throughout by 4. Okay, 4 times that, you remain with the numerator, which is 4.5 minus VTH plus 2 into 4 is 2. 2 times the numerator there, you're going to have 6 minus 2 VTH, which is going to give us a 0. Okay, upon having this, we can get this, the one with the VTH, the other side. So you're going to have 4.5, which is adding 6. This will give us, when this one goes that side, it will be equals to VTH. This one plus 2 VTH. Okay, when you add these, they are going to give us a 3 VTH. When you add this, they'll give us a 10.5. Okay, then you divide both sides by 3, begin there by 3. So you realize that your Thevenin's voltage is 10.5 divided by 3. We are going to have 3.5 volts. Okay, you have 3.5 volts as our Thevenin's voltage, which is the voltage here. Thevenin's voltage is 3.5. Okay. So our circuit has been simplified. Once you have this, then you can connect the load back. Okay, then our circuit will be has been simplified to just one voltage source, a resistor which is in series with another resistor, which is our load. Okay, so our load is 6, our Thevenin's resistor is 6, our Thevenin's voltage is 3.5 volts there. Okay, upon having this, the question was saying calculate the current across the 6 ohm resistor. So we want to find the current now which is passing through the 6 ohm resistor which is there. Okay, so how do you find the current passing through that? In short, we want to find the current in this circuit. So the current is given by voltage over resistance. But here you've got these two resistors which are in series. So find the total resistor of this circuit. RT will be 6 plus 6, and this will give us a 12. So the total current, or the current which is being produced, because we know these are in series, so they will allow the same current passing through them. So the total current is given, the total resistor is 12. Okay, so for us to find the total current in the circuit will be voltage, which is 3.5, divided by the total resistor, which is 12. Okay, this will produce a total current of, which is 3.5 divided by 12. It will give us 0.292. 0.292 amps. That is the total current which is produced from the supply. And that total current is the same current which will pass through the 6 ohm resistor. Therefore, the current passing through the 6 ohm resistor is this same one, 0.292 amps. Okay, so we've solved this question using the Thevenin's theorem. In the next